Well, I would rather die than play that game. He said no spoiling. You're still one. You know it could be. You have what? I think I ended yes. Oh wait. I'm just kidding. Yeah, I know the
could you just quickly explain normality again?
What else?
So normality is actually, depending on the context, is actually talking about acid. And actually it indicates the coefficient in front of the protons. It's actually for the base, then it's actually in front of your hydroxide. But if it's actually salt, it's actually the total number of your ionic species. Yeah, so for the H2SO4, because it produces two protons, therefore normality you have to multiply your molarity by 2. Yeah, yeah. And but for your HCl, multiply by 1. It is actually a salt. For example, 1 NaCl, normality will be 2 because it is 2 ions.
Thank you. So a question like this, right? Since this would be my target equation, I would have to flip these two, and right here, I'll just. So for right here, this is I got confused. I would just have to cancel these two terms. Is that correct?
Yeah, you need to cancel all the intermediate. So because in the end, it's actually additive equations. Yeah, the goal is actually to remove all the unwanted species in your target equation.
Thank you.
Yeah, it's like the double egg would be so. Thanks. It could be, but I still don't. Yeah, I still. No. Well, no, and there's a point. Only S and B. He's oh no, he's actually crazy. Oh my goodness. Oh dude. That's so stupid, bro. That's insane. Huge calculation I had, so everything. That's oh my god. Okay, so normality basically, it's multiplying your molarity by how many for acids, how many protons. So you did it basically that's how many hydroxide you have, and for salt, it's just how many ionic species in the is. So for NaCl, basically would be 2, right? 2 protons, bases of relations, and then all the salt is just whatever includes what the ion is associated. So for H2SO4, we only look at the hydrogen like this. The hydrogen H plus. How much wood would a woodchuck take? That's what I'm thinking. Why is there so many chunks of wood? A lot of wood. That's to throw you off. Wood. I think it's all working starting with wood. All the wood and never. That was too easy, bro. Like that one, yeah. Stilted. Aren't stilts like the giant sticky one? Yeah. I think stilted is like the hills. Maybe still use that card. When's fog? Yeah, that. Whoa! No way. That's goofy. I don't know. Ever heard of this thing. It's a cartoon character. No, baby. So solute particles and three boiling points on pressures, freeze lines on. Yeah, vapor pressure, vapor pressure goes down. If you got a something like water that's affecting concentration. Is carbonated. You could fail today. Why? I can show all this. I'm just showing you. No. There you go. Oh, it is. That's how it would go. I see. That's a good theory.
Okay, sure. So here it says, like for example, sodium carbonate association to 3 ions, but it says the equivalency factor would be 2.
They're only counting the positive ion.
Yeah, is it only counting the positive Na pluses? Or should it be 3? Is Google just wrong?
I guess it's really depending on the purpose, because acid base is actually clearly defined. And salt, I think, is actually to have more context. For example, what it's actually for. Yeah, so I guess it can be ambiguous, not so clear to define that, right? But for me, it's actually, if I'm actually given the questions, it just ask you about the ionic strengths, which both N and K will contribute to it. Then it should be 3. But if it's actually talking about some specific process only involve either the Ki or Nions, then you will go to the list specific coefficient. Okay, does that make sense? Yeah, so I guess they need a little bit more context to frame that problem properly.
Okay. Thank you.
Okay, so let's get started. Any questions before I enter into the second unit of this semester? Midterm survey is actually on Teams now. Yeah, so on the board, you can see that I brought things in so you can see this things better. Okay, so these are the things that you will focus after you finish your midterm 1. There are 2 things you can do. First is actually you can go to the first one, the partial point for your midterm 1. Okay, so the midterm will open this Wednesday or Thursday. Okay, one of the days. What you have to do first is actually go to this website, Engage, okay, and then download, make sure you download it, okay, because you need those things. Okay. Download your midterm, okay. Make sure you should display the correct answer and your answer you make sure answer wrong. Okay, so those are the things you will need for the partial question. Okay, so make sure you should download it, okay, because it will close next Wednesday or next Tuesday, actually. Yeah, which is like the deadline that we have here. Okay, so if you click your assignment, there's actually a very detailed step you need to follow. So make sure you follow all those steps. You don't put just submit your partial credit request. Okay, all of them will be graded by next Friday. Okay, so you will see your grades updated on the canvas. Okay, so that's actually first thing. Second thing is actually we're going to do the midterm survey. Okay, you're going to be asked maybe 7 or 8 questions. It's all very simple questions. Okay, and the main goal is actually let me know what is actually things that you want me to do more, so I can actually help you guys to improve your grade. Okay, so I'm going to do that. Once you turn it in, okay, then you got 1 extra bonus point. That 1 extra bonus point will be added to your final grade. Okay, so it means a lot.
Okay, it is not a point in your return, it's actually way more bigger than 1 point in your return. Okay, so make sure you actually do that. Okay, and the survey will do also next Friday. Okay, so after next week, you're going to see all the things reflected on Canvas. All right, so any question for that? Okay, if not, then also write down the things we are going to go through for the next 4 weeks. Okay, so I know it sounds crazy, but this actually you guys schedule. Okay, this is very fine. You're going to finish your midterm 1 this week, right? And then starting from this week, after 4 weeks, you're going to have your midterm 2. Okay, so that's actually a lot of things that we're going to go through for the midterm 2. Okay, so I know you can also see here, right? Most of students actually not here today because majority of you guys is going to try your best to do your midterm 1. Okay, so I will go slow for this week. Okay, and then some students should actually realize that I did not post the hangout last week, right? Because I feel it's actually pointless because nobody's going to look at it. Okay, so I want to cover most of the foundation today. Okay, so that this week after you finish your midterm 1, you can go back and watch the video, which is already, if you can understand things actually in the in-person lecture, watching video is actually quite straightforward. Okay, then next week we're going back to the normal mode that you can just watch the video over and come to here. Okay. So here I summarized the main thing for the midterm 2. Chapter 13, 14, and 15. The main thing for the midterm 2 is to calculate the pH of your solution. Okay, but before you can calculate pH of solution, one of the biggest things you must learn is that you need to know what kind of solution that you have. This is actually the first question you could ask yourself. Here you can see the questions in this pH calculation problems. Is that you want to ask yourself, do I know what kind of solution I'm having now? Okay, because at the end of this week or early next week, I will just give you the equations. I tell you, okay, if you have strong acid, calculate this way, strong base this way, weak acid this way, base that way, buffer this way. Okay, so equation-wise will be actually very straightforward. So on Thursday, we're going to tell you how you actually get to those equations. Okay, and for the chapter 13, mainly we talk about acid, base, and salt solution. Okay, chapter 14 is actually the most complicated one, which we are going to talk about buffer. Okay, and in your lab, I think you start to do maybe the titration experiment. Okay, so all the related calculations actually in chapter 14. And we're going to tell you how to actually do those titration calculations as well. Okay, but titration process will actually involve the transition of the solution properties from acid to buffer to base, or vice versa. Okay, so this is why the course is really designed in this specific way. Okay. So once we finish chapter 13 and 14, which is actually the biggest part of the midterm 2, then we're going to chapter 15. Okay, 15 is actually something about the insoluble flow. Calculation wise is actually super simple. Okay, and the only thing to be paying attention is that you actually make sure that you know how to actually get the scientific notation on your calculator. That's actually the biggest part of the chapter 15. Okay, so if you dive in chapter 13 a little bit more, what we're going to go through today is actually to tell you some simple rules that you want to memorize. So that you know when you see a molecule, you can quickly say, okay, I'm going to have a strong acid, strong base, or weak acid base, or salt solution. Okay, so those are the number one thing that you need to actually really memorize. Okay, and we're going to introduce a very, very, very important concept called a conjugated acid and base. need to learn how to write those things based on the description in the question. Okay. So after that, then the next big thing of chapter 13 is that how to calculate pH and percent dissociation of your solution, which will be the main topic on Thursday. Okay. So these are the topic for chapter 13. Okay. Any questions? No? Cool. You guys finished your midterm one already? You guys feel prepared? Okay. Have you guys actually do your practice exam? Okay. Have you actually tried to get some practice exam questions from this is something to me that you can actually get the practice exam of last year. Right? If you do, then do that too. Because that's again part of the decoding. Right. The more you do, the chances actually you're going to see those questions in your real exam. Okay. And then I hope by now you have a good feeling about what you are going to face for your midterm one. Okay. And I hope that the things I said in the past has been proven to you it is true. Okay. I just tell you how to do the things. Okay. And hope after doing this pathway that you start to see how I actually handle the problems, right? And if you have a chance to actually talk to some other PA or instructors, okay, you can compare the way I teach things to the way they teach. Okay, I hope you will see that I really try to simplify things as much as I can. Okay, which is something that you should do because you be more efficient. Okay, so practice that too. All right. Okay, so we're going to, okay, so I think that's actually what you're going to see for the rest of the semester. Okay, so do really follow the lead. I think that's like the most an easy way to get the grade that you want. All right. So get back to chapter 13. We're going to talk about acid. Okay, so people studied acid and base for extended amount of time now. So in the very old time, the first person that bring up the concept of acid is Arrhenius. Okay, so basically time, the definition of acid base is actually very simple. Species that generate protons is acid, species generate OH minus is base. Okay. So that is actually generally true for most of the things we're going to see for chapter 13 because we only talk about water solution for CHEM1312. Okay, that means actually the acid is actually species in equal to H plus, right? And the base is actually species that will eventually lead to the OH minus. So that is actually true. But when you actually become a more advanced scientist where you're going to handle the acidity and basicity of non-aqueous solution, okay, this becomes problematic. Okay, we realize that proton H plus is still fine, but not every single species can produce OH minus. Okay, that's why we actually change the definition later on. So we have a second theory called the Borstad-Lowry theory. And the way he defined the acid is a proton donor, the species that produce H plus in the solution. Okay. But for the base, instead of saying the species that will generate OH minus, we simply say the species that can accept H plus. Okay, so those are the biggest differences. Okay. And then this Borstad-Lowry theory, okay, is proton donor, proton acceptor become the most state-of-art theory of our acid-base theory. It can apply not just to the aqueous solution, but also the non-aqueous solution. Okay. I guess there's a number of use attention later, right? Because in chemistry reactions, many of times reactions are done in organic solvent, not in the aqueous solution. Okay, so these things become very important for our chemistry. Okay. So what we're going to learn today is actually how do we actually understand the concept of conjugated acid base? Okay, based on this proton donor, proton acceptor theory. Okay, so those are the first things that we need to learn. Okay, so you can see on the handout. Okay, it says a conjugated acid of species A can be defined as this. Okay, so let's say you start from a species A. You want to find out its conjugated acid. Okay, so okay, so if you want to find out the conjugated acid species of A, okay, all you do is actually you add in H plus. Okay, so when you add in H plus, this resulting species will be the conjugated acid of A. Okay, so for example, if today I give you a species called NH3, okay, so if I ask you what is the conjugated acid of NH3, so what you do is actually very simple, right? You just add in H plus. Okay, so once you add in your H plus, then you know you're going to result in NH4 plus. Okay, then we call the NH4 plus is the conjugated acid of NH3. Okay. On the other hand, you can also say the NH3 is the conjugated base of your NH4 plus. Okay, everybody follow what I just said? Okay, so this is actually a conjugated acid, right? Then this will be conjugated base. So these two will show up as a pair, always. Okay. So the difference between a conjugated acid and base is simply a H plus. Okay, so if you want to actually find out the conjugated acid of a species, the value is actually starting from your original formula, add in H and add a plus, that will give you a conjugated acid. Okay, but if you're starting from an acid, you want to find out its conjugated base, what you do is actually you subtract one H and subtract one positive charge. Okay, so everybody follow the thing I said? Okay, let's do a practice. Find out the conjugated base of H2SO4. So what you will need to do is actually you minus a H, right? So originally you have two H. So right now you know you only have one H left, right? All the other things stay the same. And then you can actually subtract one charge. So that this become, you start from neutral, which have charge of 0, right? You subtract one charge, then this become -1. Okay, so we will call the HSO4 minus of the conjugated base of H2SO4. Is that clear? Okay, so these actually things you are going to use over and over again in chapter 13. So make sure you know how to write these things properly. Okay, so let's actually the first things that you need to learn.
Second things you're going to see, it looks like a lot of things. Okay, and these are the rules that you will need to use to predict the species you're looking at. It is a strong acid, strong base, weak acid, weak base. So those are the rules. Okay. So rule number one. Okay, these are 4 rules that I summarized. Okay, you're not going to see these 4 rules in your textbook. Okay. So rule number one is actually very simple. Most of the acid and base, they are weak. Okay, meaning that if you encounter a molecule, you don't know what it is. Okay, if you need to actually guess is actually weak acid or base. Okay, they have actually a pretty high chance of getting it right. Okay. But of course, we are educated students, right? So we want to actually do a better job than that. Okay. So in order to actually improve your successful rate, okay, then this is the next thing that you need to know. You better use your beautiful periodic table. Okay. So I would strongly encourage everybody to print out this table and bring it with you. Okay. Because you're going to use that table when you do your midterm 2. Actually, in midterm 1, you also use your table 2, right? Because there's actually a lot of constants under the PR table. Okay. So print those tables out, okay, and then start to draw notes on the table. This is actually helpful because once you go into your exam room, right, you're going to have that table shows up. You can start to draw the things that you like to draw, right? Then you actually can force you to actually memorize many important points that were mentioned today. Okay, so I'm going to show you a few rules that you want to actually really know. Okay, so the first thing I say is that if the acid, I want to actually highlight this first. Okay, if your acid is actually not too crazy, okay, it's actually a binary acid or binary base, meaning actually you have a center atom, okay, and then you have H or OH minus, those kind of acid or base. Okay, so if lead is actually a base, they are going to have, okay, so the stronger acid will be the one that shows stronger acid will show up to the right, to the bottom. Okay, so if I just ask you to compare, for example, HF and HCl, okay, then you know since Cl is actually lower in the periodic table, right? So it becomes a stronger acid. Okay, so those are the something that you want to actually memorize. Similarly, okay, so periodic table is actually designed in a way that group the things actually based on its property. Okay, that's why I say using your periodic table is actually very, very good for your GEM computer. Okay, so that's actually the rule number 2. You just need to know to the right, to the bottom, stronger acid, to the left, the bottom, stronger base. Okay, this actually can always help you to solve some questions. Okay. Rule number 3. There's actually not many strong acids, strong bases you can memorize. Okay, so if you memorize this few, then you're done. Okay. 7 strong acid. And this is actually in order. Okay, so the first one that show up is actually the strongest one. HI, HBr, HClO4, HCl, HClO3, H2SO4, and HNO3. Okay, so memorize this. Those are the 7 strong acids that you need to actually memorize. If you encounter something you think is actually acid, it doesn't belong to this big 7, they are weak. Okay? Strong base. Every time you see strong base, then if you go back to your periodic table, is 1A and 2A elements are your best friend. Okay, so if you see these elements in combined with hydroxide, meaning actually, for example, LiOH, right? Lithium hydroxide, okay? Or oxide, let's say magnesium oxide, okay? Or hydride, NaH. Okay, so if you see these things in combined with OH, O, or H, they are strong base. Okay, so far so good. So that's actually the rule number 3. So rule number 4 is something called the oxalic acid. Okay, so when we talk about the oxalic acid, it's going to have this feature. You're going to see H show up in your formula, and you're going to see multiple oxygen show up in your formula as well. And then between these two, you're going to have a center atom. Okay, for example, HClO4, HClO3. Okay, so these are two strong acids of our big 7. Okay, so if you look at these two, they are actually a standard type of so-called oxalic acid. So which one is actually stronger? The answer is actually, if you do this calculation, the number of oxygen minus actually your number of protons. Okay, whoever is actually bigger is going to be a stronger acid. Okay. And the reason is actually very simple. If you're a chemistry major, right? Because you have more oxygens, you have more atoms, you can actually delocalize your electrons. Okay. But let's look at another type of oxalic acid. Okay, which means you have the same H, you have the same oxygen, but the center atom it is different. Okay, so under that case, who's going to be a stronger acid? Okay, they're actually depending on the electron negativity. Okay, the one with a stronger electron negativity, it will give you a stronger acid. Okay, but how do you know which atom has a stronger electron negativity? Yeah, so I guess we're not very familiar with that. Or are you actually very familiar with that? I'm not actually. Okay, but I do know. Okay, so this is actually why these things actually become useful. Okay, so what are the atoms that have strong electron negativity? I'll just highlight the things. Okay. The reason I want to use PR table is that it's not too difficult to memorize the pattern, right? So 4311, I guess everyone can remember that. Okay, so these are the atoms that has stronger electron negativity. Okay, so the strongest one is actually the chlorine. Okay, and then will be oxygen and then chloride. Okay, so the things you can memorize is actually your top right corner is actually the one with stronger electron negativity. We'll move down to become weaker. Okay, so whoever actually has a strong electron negativity for your oxalic acid, then it will be a stronger acid. Okay. One of the most famous examples you're going to see in your homework or maybe in your quiz is that this H3PO4 and H3ASO4. Okay, so if you look at these two, it contains your H, it contains your oxygen. So you know it is an acid, right? Then you want to actually compare what is actually center atom here. One is this guy, one is that guy, right? So you first need to know it's actually a acidic acid. Okay, because in our rule number 2, we tell you whoever goes to the bottom of the periodic table, it will be a stronger acid, right? But this way, this one is actually just the opposite because it is not just a binary acid. It is actually an acid composed of 3 atoms, right? So you have multiple oxygen and hydrogen. Okay, so under this case, it is just the center atom is different. Therefore, you actually use the electronegativity to predict the acidity. Okay, so since the phosphine belongs to the atoms that have stronger electronegativity, therefore it will be a stronger acid. Okay, so some people get confused about this order. Okay, so those are the 4 rules that you need to actually memorize. Okay, any question about these 4 rules? You good? Okay. After we know these 4 rules, okay, I want to also specifically talk about a very special base. Okay, a very special weak base that's going to show up in all the questions you're going to see in chapter 13. Okay, so that special base is called the NH3 amine. Okay, so amine is a very, very well known and widely used base in your daily life. Okay, so it will show up in various different ways. Sometimes you see this NH2, R2NH2, R2NH, or R3N. Okay, where the R represents the carbon hydrogen chain. Okay, everybody understand what I just said? Everybody is fine with when I use R to represent a long chain of carbohydrate. Okay, so you're going to see one question like this in the future, okay? Because I feel like students somehow will lose ability to see that you actually have an amine, okay? So the R is typically called the okay, sometimes you see this term R group, okay? What it means is just a long chain of CH2, CH3, okay? So, for example, if I write this, okay? So this will be my R. Okay, so every time you see this equation, what I want you to translate is that this is going to equals to your R NH2. Okay, so structure-wise, what it means is this. You have a center atom, nitrogen. Then you have this carbon hydrogen, okay? And then this one also attached to two proton. Hydrogen over there, but it will eventually accept the work. Okay, but let's look at structure. Okay, so this H can be also replaced by your archaeal chain. Okay, therefore, I put this RNH2, R2NH, and R3N. Okay, so they all mean the same thing. It's just a nitrogen atom attached to 3 R group.
okay, or 3 different moieties. Okay, sometimes the moiety is actually your edge, sometimes the moiety is actually a long chain of the carbohydrate. Okay, so this is actually a very standard and very well-known weak base. Okay, so it's just something that you just need to accept it. Okay, that's actually the definition. Okay, it's conjugated acid. Okay, this is actually a very interesting part that you must know. Okay, it's conjugated acid of this weak base, amine, will be you add in a H plus, right? So you can see that NH3 becomes NH4 plus. Okay, and then the RNH2 become RNH3 plus. This one become R2NH2 plus. This one become R3NH plus. Okay, so what it really does is that originally you have these three things attached to your nitrogen, right? Right now I add in another hydrogen, actually another proton. So let this whole thing carry a positive one charge. Okay, so once you do this, you convert this base into a conjugated acid. Okay, so it will become acidic. Okay, this acidic will be strong or weak. Strong or weak. Weak. Okay, remember, very important concept, but let's actually never actually understand this. If you have a weak acid, its conjugated base will also be weak. Okay, if you have a weak base, its conjugated acid will also be weak. Everybody follow these things fine? Now things are going to get a little more complicated. Okay, so listen very carefully about what I'm going to say. The conjugated base of a weak acid will be a stronger weak base. Let me write that. Yes, I know. But that's actually a very important concept, okay? Okay, so this is actually the first thing you should know. Okay, so this is actually a simple understanding that you should actually understand. If you have a conjugated base of a weak acid, it will be still a weak base. Okay, but conjugated base of a weak base is going to give you a stronger weak base. If you actually follow this logic, because you're going to use this concept afterwards. Okay? But basic idea is that if you start from weak, you're always going to be weak. Right? So conjugated base of a weak acid is going to be a weak base. But if you have a weaker weak base, when it's conjugated, like we use acid here. It's better to just read it so that I don't make mistake. Conjugated base of a weak acid is going to be a weak base. But if you compare two conjugated base of a weak acid, okay, then the
weaker weak acid is going to give you a stronger weak base. Okay? So this is actually a very, very important concept. Okay? So when ion factors have strong acid and strong base, under what conditions? So your strong acid is only the big seven, always. Okay, no exception. Okay, strong base is 1A, 2A group, oxide, hydroxide, and hydrogen. Okay, so make sure you understand these things 100%. Okay, because if you understand these things, actually become very simple. All right. So those are the rules that you need to actually know. Then we are going to move to another thing called the salt. Okay, a salt is actually a compound. Once it dissociates into your aqueous solution, it's going to produce K ions and N ions. Okay, so you need to actually judge the acidity of your salt based on your K ion and N ions. Okay, so the salt, once they dissolve in water, is going to produce two species. Okay. Then you can actually first judge what is the acidity or basicity of that ionic species. So then you can actually judge what kind of solution that you can have. Okay. So a few things that you should know. If you have a cation and anion that belongs to part of your strong acid or strong base, okay, it is actually the conjugated base of your strong acid or conjugated acid of your strong base. Those ions, they are neutral. For example, NaOH is a strong base, right? So once it dissociates, it becomes Na plus OH minus, right? So this ionic part, Na plus, okay, this one is actually neutral. Okay. HCl is a strong acid, right? Once it dissociates, it becomes H plus and the Cl minus. So this Cl minus is anions, okay, of a strong acid. It will be neutral. Okay, so if you see a ionic species that belongs to part of your strong acid or strong base, they will be neutral once they dissociate. Okay, so that's actually the first point you need to know. Second is that the conjugated base of a weak acid, okay, since it's actually a base, right? So it will become basic. Okay. For example, okay, HCOOH. Okay. So when you look at these things, what do you see? You see a lot of H, a lot of oxygen, right? So that is actually implication. It is going to be a acid. Okay. Then you think about this. Does this one actually belong to our big segment? Then you realize no, this is actually not part of big segment, right? Therefore, not is actually a weak acid. Okay. So since you know this is actually weak acid, then by now you should know its conjugated base, which will be COO minus, right? So I just subtract the H and then put in a negative charge. Then this one will be the conjugated base of HCOOH, right? So these things will be, again, a weak base. Okay. Third point, conjugated acid of weak base. Okay, so typically the things we're going to see is H3, right? As conjugated base, the conjugated acid will be you add in H plus, which make it NH4 plus. Then this one will be acidic, right? A weak acid. Okay, so those are the things that we need to know. Okay, any questions so far? Yes. In the conjugated base of a weak acid. Okay, so that's actually an example we give you, right? So this is actually a weak acid. Then its conjugated base will be HCOO minus. Then this species, when they show up inside the water, then it will be a weak base. So it will form a basic solution. All right, so we're going to go through a few examples so we can see this principle better. Okay, any questions so far? So if not, let's just work on the 3 questions and that's it for today. Question number 1. Okay, classify all these species. Okay, tell me they are strong acid, strong base, or weak acid, or weak base, or neutral. Okay, so first one, NH3. Okay, NH3 is actually the most important and famous weak base that you should know. Okay, so every time you see NH3, you know it's a weak base. Okay. Second, CH3, CH2, CH2, NH2. It is a weak base. Yes, how do you know? What's the part you should pay attention to? That's the key, right? Because whatever actually show up before that, it's just an R, right? So the actual point to this category are NH2, right? So like you know, it is still the same. It's just a derivative of amine. Therefore, you know it has to be a weak base. Is that clear? Everybody get what I say? How about this? Ask yourself first. Acid or base? Acid. Okay, it's actually a typical structure of so-called oxalic acid, right? You have a bunch of H, bunch of O, and you have central atom. Okay, therefore you know it is actually acid, right? Does it belong to the big 7? It's not. Therefore you know with acid. Okay, make sure you remember your big 7, okay? Simple, right? Next. RBOH, right? So apparently you see this OH indicates actually a base, right? Then you look at those elements, the septone to belongs to 1A or 2A in your periodic table. Then you should see that RB right here, right? Therefore, you know it's actually belongs to 1A. Therefore, you know it's 1A hydroxide, strong base. Okay, very last one. HClO4. You can recognize this actually one of your big saver, right? Strong acid. Okay, so if you can really memorize the rules that we just went through, then solving this type of question is actually pretty simple. Okay? Any questions so far? Yes. Very good question. So from the equation itself, you won't be able to do that. But what I'm going to tell you is called KB. Okay, the equilibrium constant, your base. Okay, so from your KB values, then you will know which one is actually stronger. Okay, short answer is actually the one with stronger KB, a larger KB will be a stronger base. Okay, so let's actually first question. Okay, let's look at the second question. So second question is actually looks a little bit trickier. Okay. Now this actually start to tie back to your chapter 12. Okay, equilibrium constant. Okay. So it says consider reaction below. Using your knowledge of relative acid-base strengths and equilibrium, determine what you can talk about the size of Kc. Okay. So this is of course actually some question that students send me. Okay. So if you actually go back and look at these questions, you have actually this a multiple choice. Okay. It's going to give you an option like Kc larger than 1, Kc equal to 1, or Kc smaller than 1. Okay. So those are the question that you will be asked. Okay. So the question, let me define this things better for you. The question is actually going to ask you, is the Kc going to be larger, small, or equals to 1? Okay, so that's the question. Okay, so how do you actually solve these things, right? The first thing to actually think about is that when we talk about Kc in chapter 12, we always say the Kc is a ratio between your product over reactant, right? So product over reactant is actually things that we defined previously. So Kc is actually product over reactant. Okay. That means actually if you have more product, then your Kc will be larger than 1. Otherwise, your Kc will be smaller than 1. Okay. You will equal to 1 only when you have equilibrium. Okay, meaning you have the same amount of when it's at equilibrium, that's actually that's where to put it. Okay. So now it gives you these equations, right? The equation is H3 SbO3 plus HTeO3 minus becoming H2 SbO3 minus plus H2 TeO3. Okay, so I want you to actually pay attention to this equation. So tell me, do you see conjugated acid-base pair inside this equation? How many pairs? 2 pairs, right? So let's actually the first thing to actually highlight it. Okay, you should see this and this. This is actually a pair, right? And then you should know that who is actually the acid, who is actually the base, right? So you know the acid is actually H3SbO3, right? And then the second pair is this 2. And then when you look at it, you should see that this is actually the acid, this is actually the base, right? So up to this point, you should see that you have 2 acids. One is actually on the left, one is actually on the right.
Okay, and they want to actually compete against each other. Okay, let's say if your H3 SpO3 is a stronger acid, then you know dissociation of it will actually happen, right? It means actually the reaction is going to push toward the product side. On the other hand, if your H2TeO3 is a stronger acid, then the reaction will move to the reactant side. Okay, so if the reaction moves to your reactant side, then your Kc will be smaller than 1. Everybody follow what I say? Okay, so it's really, this is actually a very technical way to actually to compare the strength of these two acids. Okay, in a way that disguise using Kc as a parameter. Okay, so now you need to actually make decision. Which one is actually stronger? So typically when you see these things, right, you see multiple oxygen, multiple hydrogen. It's actually oxalic acid, right? And then the other thing is what? The center atom, they're different. Okay. So the best way to actually do that is actually go back to your periodic table. What are the two atoms we're actually talking about? One is what? So Sp and Te, right? These are the two. Okay. So apparently, if you use the rules that we have learned, okay, what would you say? So Te is actually to the right hand side, right? So in principle, it should be the stronger one. Okay. So that's actually one thing we can actually make the judgment. Okay. Second, okay. For the, so we're going to talk about oxalic acid. They have two rules, right? One is actually the center atom are the same. Then compare the difference between the number of oxygen molecule and number of hydrogen. That's actually one rule, right? The second rule is actually based on the electron activity. Okay, so if you look at this two, it doesn't actually belong to those really strong, the atom with strong electron activity, right? So under that case, you actually go back to the simplest rule. Whoever is actually over down or over right of your PR table, they will get a stronger acid. Okay, so with that being said, therefore we know. Yes, I want to write it side by side. Therefore, you know your H2TeO3 will be a stronger acid, right? So this actually, if you rank us based on its acidity, right? So once you know that, you know this one is going to dissociate, right? Means it's going to push the reaction to the left. Okay, meaning produce more reactants. Therefore, you know your Kc will smaller than 1. Okay. Any questions so far? No good? Then I want to ask you a question.
its conjugate base, which is H2SbO3 minus, and then HTeO3 minus. In terms of basicity, which one is stronger? Hmm? So remember the things we just talked about, the very complex sentence we went through. Where do I write it? Oh, this here. Conjugated base of a weaker acid will be a stronger base. Okay, you need to actually get used to these things, okay? Conjugated base of a weaker acid will be a stronger base. Okay, so with that being said, let's come back to this. This is actually a conjugated base of a weaker acid. Therefore, it will be a stronger base. Okay, so you actually get familiar with this type of thinking. Okay, and this is actually a thing that we encounter a lot in chapter 13. It's not difficult. You just actually figure out, okay, what's the actual correct concept to use. All right. So the very last question we want to go through today will be this. In an aqueous solution of NaNO3, is it acidic, basic, or neutral? Okay, so how to handle this type of question? Okay, the first thing first is that you need to recognize that the things you have is a salt. Okay, so how do you know you have a salt? The best way to recognize you have salt is what? Yeah, you have this 1A group element, Na. Okay, or you have the 7A element, right? The fluoride element. Okay, those species typically show up in the salt, right? So if you see a compound and you see those species, okay, then think about your salt. Okay. So the first one, NaNO3. So in this chapter, you actually used to write out this dissociation equation. Okay. Na always carries positive one charge. Okay, so then put everything remains together. In the beginning, U is neutral, right? So the charge is actually 0. Therefore, you need to put -1 for your NO3 for your NO3. Solid left and right will equal. Okay, so once you write this down, then you look at this. Na plus. Na plus is part of your strong base. Therefore, it is neutral. Okay. NO3 minus. NO3 minus is actually part of your HNO3. HNO3 is a strong acid. Therefore, this one is actually neutral. Neutral, therefore this will be a neutral solution, neutral salt solution. Is that clear? Okay, so really actually start to differentiate, okay,
for your amine species, are they neutral, are they weak acid, are they weak base? Okay. So let's actually for the NaNO3. Second, NaCH3COO. Again, you see this 1A element, right? Therefore, you write out Na plus and put everything remains CH3COO minus, so that 1 plus 1 minus, it will equal to the neutral state. Okay. So once you have your cation and anions, then you start to make another judgment, right? Sodium, again, part of your strong base, therefore neutral. CH3COO minus. Okay. So every time you see this minus, right? Most of the time it is actually a base. Okay. But a more proper way to think about this is actually, okay, the conjugated acid of this species is CH3COOH, right? Its conjugated acid is CH3COOH, which is actually a weak acid. It is not base 7, right? Since it's actually a weak acid, therefore you know its conjugated base will be a weak base. Therefore, inside your solution, you have a neutral sodium plus. You have weak base CH3COO minus. Therefore, you know the solution you're going to have will be a weak base solution. Okay. Third example, C2H5 NH3 ER. Okay, very long chemical formula, but you see this ER at the very end, right? So BR once you actually dissociate, you know it's going to give you BR minus, right? And BR minus is actually part of HBr, which is a strong acid. Therefore, you know this guy is actually neutral. Okay, so the remaining part will be C2H5 NH3 plus, right? So if you look at this C2H5 is just a R group, right? Therefore, it is actually RNH3 plus. RNH3 plus is actually the conjugated acid of RNH2, right? So RNH2, which is actually a weak base by itself. But this is actually a conjugated acid of a weak base, right? Therefore, this one is weak acid. Therefore, inside your solution, you have a weak acid species and a neutral species. Therefore, you know the salt you're going to have will be a weak acid solution. Okay. So this principle is very, very simple. If you know it, then you definitely get used to it. Okay. So this is actually how you solve this relative acidity basicity type questions. Okay. So in your homework, in your quiz, and your midterm, sometimes they're actually starting from base, okay, which is sometimes confusing. Okay, so I would encourage everybody to think from the acid perspective. Okay, make it consistent, then you minimize the chance of making a mistake. Okay, so we'll stop here, and if you haven't finished your midterm one, good luck with that. Okay, thank you. I would encourage you to actually bring out your printing out your table to the class, right? And then because when you go through the returns, they'll give you actually one sheet with the PR table and all the constants, right? But if you're already familiar with how to draw, like the pattern I draw on the PR table, it's very easy to replicate all things on the sheet you cover. Yeah.
I have a question. So, when does the midterm survey open?